Welcome to another great day of chemistry. We are going to be focusing on the very basic structure of atoms today. So if you'll get out your study guides and turn to lesson 3, the atom, we'll get started. All right. As usual, just follow along as we go through the notes in your study guide. So if you remember, all elements are composed of atoms. And so before we go any further on our discussion of elements and matter, we need to look at the very basic structure of the atom. So first of all, as it states in your study guide, going back, sorry. As stated in your study guide, in the modern model of the atom, we can essentially visualize the atom as in this such manner. You have these negatively charged, very small, almost incomprehensible electrons that orbit or move around a very dense nucleus that is formed by protons and neutrons. Now, almost the entire mass of the atom is concentrated in the very center, which is the nucleus of the atom. Again, where those protons and neutrons can be found. And yet the nucleus is so small compared to the overall diameter of the atom. In fact, the diameter of the atom is more than 100,000 times that of the nucleus. The rest of the atom is mainly empty space with electrons moving around that nucleus at inconceivable fast speeds, super, super fast around the nucleus. As we go through the year, we'll talk more about the protons, the neutrons, and these amazing electrons as we begin to understand more about chemistry. So let's use an analogy here. Let's say we think about the atom in terms of a college football stadium. Now, if you've ever been to a college football stadium, they're large. They can fit 100,000 people in some of these large football stadiums around the country. So let's think that we take this really tiny atom that we can't even see with our eyes at all, and we are blowing it up to a large scale football stadium, college football stadium. All right. Now, let's say that the outer boundaries of this football stadium is also the outer boundary of the atom at this blown up scale level. Okay. So if you're in the football stadium and you're in the stands, you're going to be looking over the football field. And in the middle of the football field is the 50-yard line, and I think most of you know that. And then on either end, we have the end zones where touchdowns are, touchdown is. Okay. So let's say that on the 50-yard line, we place our nucleus of our atom. So what would be the size of a nucleus in a large football stadium to scale? And it would look something like a very small marble sitting there at the 50-yard line. Okay. In fact, if you're out in those stands, you're probably are not even going to notice or see that marble. It's so small compared to the overall size of the stadium. In other words, what we're saying is the nucleus is so small in the atom, so teeny, teeny, tiny compared to the overall space that the atom takes up. Okay. Now, where are the electrons? Well, the electrons are these little specks of dust that you would barely see in the stadium. In fact, you probably wouldn't even see them. They're so tiny little dust particles whizzing around the stadium at extremely high velocities. And the only way that you probably would even see these specks of dust or these electrons in the stadium is because they periodically release light. Okay, so you would see these light flashes, and where those light flashes are coming from are from the electrons as they're whizzing around that football stadium. Okay, so I'm just trying to give you a perspective of how small the nucleus is compared to the overall size of the atom, and really also how small those electrons are as well within the atom. Okay, so now let's kind of take a look at a picture of an atom or atoms. We cannot see atoms with our eyes. Okay, we can't even see atoms with a normal light microscope that you would use in a biology class or something like that, where you could see cells and other things. Atoms are too small for that. They are so teeny, teeny, tiny that we have to use a very special type of microscope called a scanning electron microscope to even begin to see the surface of these atoms. And so this picture here is directly from a scanning electron microscope that shows the very surface structure that we're of atoms. So we're barely starting to see them. Okay, but we don't get a lot of detail, a lot of clear resolution about really what an atom looks like, and really much of its structural detail of the nucleus of the atom, the electrons, the protons, and all of that stuff. Okay, so let's dive into what the basic structure of the atom would look like using a model. Okay, now since we can't see these atoms, we have to somewhat build a representative model, what we believe that the atom sort of looks like. Okay, and again, this is just a model. In fact, the model we're looking at is not completely to scale, and it's not even the most accurate, up-to-date model that we actually have. But this model that we're going to look at here, that's in your study guide, is one that we often use to help us to learn the basic structure of the atoms. And so sometimes we'll call it the shell model, and others times we'll call it the Bohr model, after Niels Bohr, who actually developed this model. And we'll talk more about Niels Bohr and his development of the model later on. All right, so here we go. And I think most of you have some understanding of the basic structure of an atom already. So to point a few things out as we kind of, I don't know, look at this structure. I'm going to kind of do some drawings here as well. So in the nucleus, we have our nucleus here, right? In the nucleus of the atom, we're going to find our protons and our neutrons, as was mentioned. So the protons and the neutrons. Now, to give you kind of a scale size of how small a proton is by mass, the proton's mass is 1.6726 times 10 to the negative 24 grams. Can you even comprehend how small that mass is? It's mind-boggling to me, the size of a proton. It's just so unconceivably small. And again, we're going to find a proton and we're going to find the neutrons in that nucleus as indicated in this diagram here. Okay, now where are the electrons? Well, the electrons are found outside of that nucleus, orbiting or moving around in some fashion, as we'll describe a little bit later in the year. But those electrons, they're found in locations that we call electron shells or energy levels, okay, as pointed here. And in this diagram, we're show only 2 electron shells, and often we'll indicate those electron shells by using the symbol N, and then equals to whatever number that electron shell is. The one closest to the nucleus is referred to as the first electron shell, N equals 1. And then the second one would be considered N equals 2. Sorry, it's hard to do with a mouse. Reset, so N equals 2 on this. Okay, so N equals 2. All right, so the first electron shell, second electron shell, and then there can be a third and so forth, as we will address later on. So electrons, as indicated by this model, are found in those electron shells, and there's going to be only a certain number of electrons that can fit in a particular electron shells, which we'll also talk about at another date. So typically all atoms can only fit 2 electrons in the first electron shell, and then in the second shell you can have a maximum of 8 electrons in that shell. All right. Now, as far as a scale or size of an electron, the mass of an electron has been found to be 9.108 times 10 to the negative 28 grams. All right. That's much smaller than a proton, much smaller. In fact, a proton is roughly, you might want to write this down, a proton is roughly 2,000 times larger than an electron. So if we're having a hard time visualizing the size of a proton, an electron, I don't know, it's just inconceivable how small these electrons are found in these atoms. Just teeny, 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 tiny. As we said with our football analogy, the nucleus, which holds these protons in the first place, is about the size of a marble, and the electrons are just getting these little specks of dust there. Okay, so this shell model or Bohr model, all I want you to do right now is know the basic component structure of the atom, where the nucleus is, the fact that the nucleus is made up of protons and neutrons, and the electrons are outside of the nucleus in electron shells or energy levels, and the electrons, there's only a certain number of electrons that can fit in these electron shells, as we'll see later. All right. All right. So let's move on here to our next slide. Maybe. All right. So this is our last bit of notes for this particular video. I just want you to fill out this table. We'll talk a little bit about some of the characteristics of the subatomic particles of the atom. Now, when we use the term subatomic, we're talking about particles that are smaller than atoms themselves, okay? So they're also sometimes known as elementary particles of matter, but we will refer to them as subatomic particles, smaller than the atom itself. So the neutron, some characteristics to look at is the neutron has no electrical charge, and so we consider it neutral. A proton, on the other hand, is positively charged and carries a positive electrical charge. The electron has a negative electrical charge, and we'll discuss the implications of the proton and electron charge later on. Now, the relative mass. Now, since the mass of a proton, neutron, and electron, and by the way, I failed to mention this, the mass of a neutron is roughly or basically the same size of a neutron. They're almost similar, okay? But because they're so small, we're using very small quantities in grams, we have created another unit of mass for these subatomic particles called the relative mass. And so what we've done is, since the proton and neutron are relatively the same size, we've assigned a single proton to have a relative mass of 1 AMU, okay? And so this 1 AMU, which is referred to as atomic mass unit, okay? And you might want to write that down to remember that. And AMU stands for an atomic mass unit. And really, the proton is not the size of 1 AMU as far as a mass scale of grams, but for us, we're saying that a proton has a mass of 1 AMU, and it becomes handy as we work through problems with atoms later on. All right, and a neutron, because they're the same size, is also assigned a relative mass of 1 atomic mass units, or 1 AMU. Because the electron is so small, really, really tiny, an unconceivable amount of mass, we've essentially assigned the electron as a 0 atomic mass unit, or 0 AMUs. What this indicates to us is that the electron really does not contribute to the mass of the atom, really. The main contributors to the mass of the atom is the proton and the neutron, okay? Proton and neutron. So when we think of what creates mass for the atom, we're thinking in terms of the number of protons and the number of neutrons in the nucleus of the atom, not the number of electrons, okay? Now, as we just mentioned earlier, the protons are going to be found in the nucleus of the atom. Neutrons are also found in the nucleus, and then electrons are in those electron shells or energy levels. All right, so that's basically it for this video and for your notes in your study guide. Just go back and really review. Take some time to get familiar with the basic structure of the atom. So we're going to need to understand that basic structure as we go on from here, okay? So that's it for today. Good luck, and we'll see you later.